And one of our suggestions in the paper was to take advantage of long-term data sets where they exist and really try to see if we can understand recovery timescales and trajectories to see if that could be more informative of this recovery process, because these types of data were not available in the papers that we reviewed. And I think what I was particularly inspired by was this paper by Carlos Duarte and others in 2008, Return to Neverland. And here they conceptualized 4 different response trajectories that ecosystems can make when you change nutrient inputs, which are shown on the x-axis, and then a response variable. In this case, they're showing chlorophyll, but it could easily be nutrient concentrations or such. So in the upper left-hand corner, they describe their Neverland kind of situation where the degradation and the recovery trajectories are pretty much the same. They're linear and they pretty much follow each other. Then in the upper right-hand corner, you can have a regime shift or time lags. So you ultimately get back to where you started, but via a different pathway. And then in the bottom left corner, you have shifting baselines, where you end up at a point, but it's not quite where you started from. And this is potentially due to other factors, perhaps climate change or just a fundamental change in the system. And then lastly, in the bottom right corner, you can have some combination of that. And I was particularly excited about applying these ideas to the Baltic Sea, which happens to be a particularly data-rich region. And I want to share those results with you today. So just by way of background, the Baltic Sea is a large brackish sea in northern Europe. Just for context, the water volume of the Baltic Sea is slightly less than that of all 5 North American Great Lakes combined, just for context. There's about 90 million people in the catchment, and the Baltic Sea is particularly prone to eutrophication because of its enclosed nature and because there's relatively poor connections with the North Sea for exchange here via the Danish Straits, which are narrow and shallow. And so, as I said, it's particularly vulnerable to eutrophication. Water residence times are on average about 45 years. But what is, I think, amazing about this system is that we've had tremendous results in terms of nutrient load reductions. And so what I'm showing here is a combination of reconstructions up until about the 1970s, where we have better monitoring data, and it is tremendous. These are total external loads to the sea, nitrogen in green and phosphorus in blue. And for nitrogen, that's about a 42% reduction from the peak loads, which were in the 1980s, and phosphorus was a reduction of about 56% or so. And so I looked at that and I see, like, this is a huge success. And it's something society really needs to take credit for. But within society in the region, what seems to be the focus is this. And that is, well, the sea is eutrophic. And this just happens to be the cover of the most recent holistic assessment of the environmental status of the sea by HELCOM, this Helsinki Commission, the treaty-based organization which manages the Baltic Sea environment. And this is based on the most recent scientific data available, very well grounded, but it shows, eutrophication is still a problem, and it really hasn't changed in the past 6 years since the last assessment. So it's kind of within this context, I thought, well, maybe if we look at some longer-term data, we can get some more insight and add to this story versus just a snapshot of what it looks like today. So I used this approach described by Jakob Carstensen, where you start with a null hypothesis, and basically this would be, I think, the Neverland scenario, that you have nutrient loads, on the x-axis, you have some response on the y-axis, and they follow degradation and recovery follow the same linear trajectory. Then there's an alternative hypothesis where it's not linear, and there's this addition of this a second parameter that's like a smooth time parameter to take into account the time dependency of the response variables. And we did this analysis using generalized additive models in R, and the significance of the null hypothesis can be tested using likelihood ratio tests. So what I want to share with you is some results for 3 metrics that we looked at in the sea, just for one area of the sea, the Baltic proper, which I would say is like the central part of the Baltic. But I did this analysis probably for over 50 a combination of regions and response variables. So to start, so this is showing on the x-axis external phosphorus loads to the Baltic proper, and then we have, in this case, winter DIP concentrations. And just to orient you, in all of these figures, I've labeled the starting date of the time series, in this case 1970, the end date 2015, and then when peak nutrient loads occurred in 1981. And so visual inspection, as analysis further shows, yeah, there's really not a relationship. It's a shotgun blast. But when we add the alternative hypothesis, we get a trajectory that looks like this. I'm struggling to try to articulate what the shape looks like. It gets a little kind of wonky in here, but we do have better explanatory, I guess, value with this approach, and we can firmly reject the linear relationship in this. And then just for reference, I put in the target here. This is the green star. So these are the recovery targets identified in the Baltic Sea Action Plan, and similarly kind of embedded in the Marine Strategy Framework Directive. And these are based on pre-eutrophic, I would say 1930-ish, 40 type conditions. And the goal is to achieve these targets by 2021. So next, let's look at, again, we've got the same external phosphorus loads on the x-axis, and then we have chlorophyll A on the y-axis, and just a quick visual inspection shows it's kind of not the direction we would expect. It shows a negative relationship, and indeed that is what we see. But if we add the gamma analysis, the alternative hypothesis, we can see, I guess this looks more like kind of like a boomerang, that we have upward trajectory here and then recovery kind of going in this direction. Again, we're making progress towards external nutrient load reductions, but again, there's quite a gap from where we want to be in terms of summer chlorophyll A concentrations and where things currently are. And then lastly, just because I love nitrogen, we'll look at a response for nitrogen. So here are external nitrogen loads to the Baltic proper, and then annual average TN concentrations in surface waters. And it's, again, we see from the last graph, this kind of looks like it'd be a negative relationship, and sure enough it is. And again, when we plot the alternative, I'm again at a loss of how to describe this particular trajectory, except it clearly doesn't show like things are really getting better, but we can explain more variation in the data by using this approach. But again, even though we're getting close on these external nutrient load targets, in this case nitrogen, we still have quite a gap as far as where we want to be. And if we look at computer modeling that we have for the sea, biogeochemical models, those suggest that, hey, it just takes time. It'll take 30, 40, 50, 60, whatever years, and we can eventually get here once we hit the external nutrient load targets. So it suggests, the models suggest that we're not in a shifting baseline type phase. Now, but if we extract just the generalized shapes that I showed you in the previous pictures or slides, and then compare them with the original Neverland paper, I mean, about the best I can say is it's really messy. And this is really frustrating, I think, because, as scientists here, we have nearly 50 years of data, and we can't distinguish between time lags or shifting baselines. And it's particularly frustrating, I think, for society in Sweden as well, because what's perceived as this non-recovery has really led to kind of persistent calls for a massive, large-scale geoengineering to restore the sea. So we've been really struggling with, is there a better way to articulate recovery to give the sense that we are making progress? And so we've been playing around with this idea of accumulation to depletion. And so what I'm showing here are model-derived total nitrogen pools in the water column and in what I'm saying active sediments for the entire sea. These are from the BALTSEM model. It's Baltic Sea eutrophication model. We have a lot of confidence in this model. It's been well calibrated, and it reproduces the data I showed on the previous slides, and it's also used by the Helsinki Commission to estimate nutrient load reductions to meet environmental targets. So kind of using this approach, we can see that, total nutrient or nitrogen accumulated in the sea until about the mid-90s, where it peaked. And at this point, forward, we see that processes like denitrification and sedimentation are finally starting to remove the nitrogen that's collected in the sea. If we look at phosphorus, it's not quite such a rosy picture, but at least we could say, well, it's not getting worse. We know the residence time of phosphorus in the sea is a bit longer, and given issues with hypoxia and some intense kind of recycling between the sediments in the water column and in the deeper areas, I guess isn't totally surprising. But we're thinking, well, maybe this is a way that we can at least articulate, some improvement. We're on the right track. So, as far as where this leaves us, I think I was a little naive in hoping that long-term data sets could add some sort of nuance to our understanding of eutrophication in the Baltic Sea, and maybe the sea is an exception owing to its slow response times, especially in hearing other talks here at this conference. When I hear about the North American Great Lakes, with the exception of Lake Erie, they seem to really be, there's measurable responses, improvements to nutrient load reductions that we don't see here. And it really begs the question, at least in the case of the Baltic, of why are we chasing these reference values? And it just really sets the situation up for disappointment on the point of society, and the sense that there's a failure in management when the nutrient load reductions have been fabulous. They really are, it's a success story. So I guess where we're thinking now is, and I'm taking inspiration from the plenary speaker the other day, talking about the brand of science and what we can offer. And so I'm thinking that, well, okay, maybe we can offer some hope, and that using a simple metric like accumulation versus, to a depletion stage, that, we're on the right track. And that's about, that's what we can say at this point. So with that, thank you. I can't see. Yeah.
Given the climate warming or climate change, and then the in-sea nutrient concentrations don't decline, probably at least at the coast, it looks worse than it looked before.
Yeah, climate change is definitely a factor as well. And that's not embedded in the targets that have been established by HELCOM. So even further nutrient load reductions could be needed to meet the environmental goals. All right, well, thank you.
All right, I'm turning the mic on over here. The next talk is canceled. Ask your editors anything.
But before you do that, we have priceless treasures in this box. But you have to have
A ticket.
a ticket.
Grab a ticket.
Does anyone not have a ticket?
You need to be in this room at what time? 5 o'clock?
A ticket for you. Who else needs